Hello and welcome back once again to this lecture series on aluminum based alloys and metal matrix composites. So far we have learned about pure aluminum and its properties. Then we have also seen different types of aluminum alloys such as cast alloys and wrought alloys. And we have also talked about the alloy designations. And then we started talking about the physical metallurgy aspect of aluminum alloys, and that is what we have been discussing in past few lectures. All right, so right now we are discussing about the strengthening mechanisms. And with regard to this, we have already discussed about solid solution strengthening. And while discussing about the effect of the alloying elements or the solute atoms, we have already seen that apart from strengthening, they might also give rise to some other phenomena. For example, this dynamic strainaging that we talked about. That results from an interaction of the solute atoms with dislocations, right? So today we are going to start one more topic on this particular aspect of the physical metallurgy of aluminum alloys. We are going to start this precipitation hardening as one of the other strengthening mechanisms that we have. This also goes by the name edge hardening. So you have seen out of the several aluminum alloys, some of them are heat treatable and some of them are not. So when you see heat treatable aluminum alloys, it essentially means that they are precipitation hardenable. Right? And we have seen that the 6000 series that is aluminum, magnesium, silicon. The 2000 series that is aluminum, copper. The 7000 series that is aluminum, zinc, and the 8000 series or the aluminium lithium alloys, these are the heat treatable aluminium alloys, right? So the precipitation hardening will apply to these alloys only with regard to the aluminium alloys. Okay. So let us first understand what is the mechanism of the precipitation hardening, and then we'll come back to these alloys and talk about them in little more detail as to what are those precipitates in each of these alloys which lead to the strengthening. Okay. The fact that only few alloys are precipitation hardenable points towards some requirements that the alloy must be having in order for them to be precipitation hardenable, right? So the main requirement for any alloy to be precipitation hardenable is as follows. It is basically about a particular alloying element or a solute atom which should be having some solubility at room temperature, and for it to be precipitation hardenable, for the alloy to be precipitation hardenable, this solubility should increase with temperature. That's the main requirement. Because every alloy would have this requirement fulfilled. The first one, that means it will have some solubility because it's an alloy, right? So it will be able to dissolve some amount of the alloying element or the solute atom. But for it to be precipitation hardenable, that solubility must increase with the temperature. Okay. So if I want to illustrate that, that can be shown with the help of the phase diagram also. In which we plot the temperature against the composition, as you know. So as I said, the solubility should increase with the temperature, and therefore the line which represents the solubility should be having a positive slope like this. Right, so this line which separates this single phase region with the two phase region, that is known as the solver's line. So this line should be sloping up like this, because the requirement here is the solubility should increase with increasing temperature, right? So you can see at any given temperature, if you look at the solubility, let's say here, it has a particular amount of the solute, let's say C1 at temperature T1, and if you increase the temperature to T2, which is higher than T1, then the concentration also increases, right? When T2 is greater than T1, C2 is also greater than C1, right? So this is the requirement which has to be satisfied. And why is that so? That is something that we need to understand now, okay? So this is the single phase field alpha, where alpha is the solid solution of the parent metal with the solute atoms that you have, right? So this composition is in terms of weight percent B, where B is the alloying element, right? Which can be any of this that we talked about, these elements which give rise to the precipitation hardening, such as copper, zinc, magnesium and silicon, and lithium. Okay. So in case of aluminium, copper, if you talk about this particular alloy, then alpha is a solid solution of copper into aluminium, right? So copper has certain amount of solubility in alpha at a given temperature. And as you could see, as you increase the temperature, the solubility of copper into aluminium increases. Okay. So alpha is the solid solution between aluminium and copper, right? So this will be the two-phase field region. In case of aluminium copper, it will be alpha plus the equilibrium phase, which is the theta phase, CuAl2. Okay. So at room temperature, let's say somewhere here, it has a particular composition, some amount of copper that can be dissolved in aluminium. And now if I increase the temperature, let's say I am somewhere here, then the solubility is much higher. Okay. So in order to do the precipitation hardening, what is done is the alloy is heated to this single phase field region to a higher temperature somewhere here, and then suddenly cooled or quenched. Right? It is heated to the single phase field region followed by quenching in a liquid so that it cools down at a high cooling rate, right? So this heating to the single phase region That is the first operation in the precipitation hardening treatment or in the heat treatment which is applied to these alloys for the precipitation hardening, and that operation is known as solutionizing. So this is the solutionizing temperature, which we can call as TS. Also known as solution treatment. So now if you cool this at a very high rate, by quenching it in a liquid, then whatever concentration of the solute atoms you have at this particular temperature will be retained at room temperature, right? So when it comes down to room temperature after the quenching operation, it will be a supersaturated solid solution. In short, we write it as triple S. Okay? Because the solubility of the alloying element is much lower at room temperature compared to this solutionizing temperature, right? Because we have already discussed that the solubility increases with temperature, right? So the solubility of the alloying element at the temperature Ts is much higher compared to that at room temperature, right? So if you suddenly cool it down from Ts to the room temperature, this concentration at Ts will be retained at the room temperature, and since the room temperature solubility is much lower, the material will become supersaturated, okay, in terms of the concentration of the alloying element, okay. So the quenching operation will give you a supersaturated solid solution if you cool it down to the room temperature. Okay, so let's say this is the temperature to which it is cooled. Now the question would be, if we do not cool it fast at a rapid cooling rate, then what is going to happen? Will the precipitate form in that case? Well, if you do that, the precipitate will actually form when it crosses this particular temperature. Let's call that as Tn, which is the temperature when this will cross the solvus line as you cool it down from the high temperature. Okay. So as it crosses this temperature Tn, if you cool it down slowly, the precipitate will actually form, but it will be a much coarser precipitate, unlike the fast cooling in which the precipitate that you get is much finer. Okay. Right, and as you know, finer the size, higher is the strength or the hardness. So here, although you will get the precipitate, if the cooling rate is low, the hardness or the strength will be lower because the precipitates will be coarse in size. Okay. And there is always a possibility that these precipitates will tend to nucleate by heterogeneous nucleation. Since the cooling rate is low here, the nucleation rate will also be lower. So it will always look for sites in which the nucleation can occur easily. And that is what is known as heterogeneous nucleation, where the nucleation occurs in preferential sites. Okay. So in this particular case, where you have the precipitate forming in an alloy, the grain boundaries can act as the preferential sites for the heterogeneous nucleation to occur, and therefore these precipitates will form as a grain boundary phase. And this is not good for many of the properties such as the fracture toughness. If you have a phase forming along the grain boundaries, it can lead to intergranular kind of fracture, and that can lead to a decrease in the fracture toughness, right? So that is another issue that you might have when the cooling rate is low due to the formation of these precipitates along the grain boundaries. Okay. And why this happens, as to how this cooling rate decides this, can be understood with the help of a diagram known as TTT diagram. I suppose you have heard about this. It stands for time temperature transformation. So it basically describes a particular phase transformation with respect to time at a particular temperature, right? So you might know it appears like a C curve when you plot this temperature versus the time. It appears as a C curve like this. In fact, you have two of them. One for the start of the transformation, and the second one is for the finish of the transformation, right? So if you are talking about this particular phenomena, precipitation hardening, then what we do first, we take it to a higher temperature where you have a single phase. So we hit it to the alpha phase region, and then we cool it down from there. Okay. So if you cool it down with a cooling rate like this, this is a very low cooling rate, then it will go through both the start as well as the finishing curve, right? And this will lead to the equilibrium phase. When you finally cool it down to room temperature, the equilibrium phase will form. So if we again take the example of the aluminium copper system, this is the theta start curve. Theta is the equilibrium phase in that case. and this is the two-phase region, alpha plus theta. And when you come to this finish curve, the transformation to the theta phase will be finished, will be completed. Okay. So if you have low cooling rates like this, then you will always end up with this equilibrium phase in core size. On the other hand, if you have a cooling rate such as this one, which can avoid the nose of this TTT curve, then this will lead to a supersaturated solid solution. And if you now heat this supersaturated solid solution after the quenching operation to a certain higher temperature in the range of 100 to 150 degrees Celsius for the aluminium alloys, then a precipitate will form which will be much finer. So this explains the need of the quenching operation. Okay. Right. So the first requirement, of course, was the solubility, which should increase with temperature. And second, when you go to the single phase region, when you heat the alloy to the single phase region, it has to be cooled down with a high cooling rate so that a supersaturated solid solution can form. Okay, so that's the other requirement. So the three basic steps that we have for precipitation hardening. First, as we have seen, solution treatment, that is heating to the single phase region. This is followed by quenching. And finally, you will have to heat it at certain temperature for a certain period of time for the precipitates to form, and that operation is known as aging. And that is why this is also known as age hardening. Okay. So now that we have already discussed about these two, solution treatment and quenching, we can proceed to discuss about the aging operation. But that will be taken up in the next lecture. So for now, I'll stop here. Thank you for your attention.